This is another trick question, that zinc actually has a single valency, which is a +2 valency. It makes a zinc 2 plus ion, whereas scandium, it has multiple valencies, so it has +1, +2 and +3, but more importantly, it is able to make the +3 ion as well. So zinc, although it is more lower down in the D block, so it has several D electrons, if you will. So you would think that it would exhibit multiple valencies, because the d orbitals, lot of electrons in the d orbitals, they can participate in bonding. So why does it have only one valency, whereas scandium, it has so many valencies, but it is the first sort of the element of the D block. So the reason actually for this, we have to look at both of these elements, zinc and scandium and zinc, in the periodic table. We have to understand where they are, and we have to understand their electronic configuration. See, electronic configurations are very important. Any and all questions about the valencies can actually be answered. Not surprisingly, they can all be answered by looking at the electronic configuration. So scandium, the electronic configuration is actually very simple. It is not very difficult. It is the first element of the D block of the fourth period. So that is what we would think the electronic configuration is, and that is indeed it is. So nothing complicated there. The zinc is the last D block element of the fourth period. So because it is fourth period, we know that the 4s has to be there, and then of course then we have the 3d electrons, which is the 3d10. So that is the configuration for zinc. Now in the case of zinc, the only valency it exhibits is one where it has lost these 4s electrons. So we can have zinc 2 plus ion, whereas in the case of scandium, it exhibits all possible valencies. So it can lose these 4s electrons, it can also lose the 3d1 electron, and it can also lose all of those 3 electrons, and therefore it exhibits all, scandium exhibits all +1, +2 and +3 valency. So my question is, why is that? Why does zinc not lose the 3d electrons? Now that is the question that we have answered. So the reason for that we have answered in another class, in which we have talked about the exchange energy. On Doorstep Tutor you can find these lectures, doorsteptutor.com, okay, on our website. So scandium, in the case of zinc, the completely full 3D subshell, it has lot of exchange energy, because there are 5 electrons in the up configuration which can exchange among themselves, and 5 electrons in the down configuration which can exchange among themselves. So these orbitals, because of this exchange energy, they have become very stable, all of these d electrons, and therefore zinc does not lose. It likes to keep these d electrons, and the only electrons that it can possibly lose are those 4s electrons. So those electrons are lost, and we get zinc +2, okay, or zinc 2 plus. Now note that this s orbital, the 4s orbital, is also completely full. The s shell is also, so s subshell, the 4s subshell is also completely full. But even then, the zinc, if it has to lose electrons, if it has to bond, then it would prefer to lose electrons from here rather than to lose electrons from 3d, because of this lower exchange energy of the 3d subshell. Whereas in the case of scandium, because there is only a single electron in the d orbital, there is not so much stability because of exchange of electrons. That energy is not lost, and therefore the scandium readily loses its d electrons. And of course these s electrons are also not so readily, but they are also lost to create these multiple valencies of the scandium, and it can exhibit the valency where it has lost only the 3d electron, which is scandium plus, and then it can also exhibit those valencies in which it has also lost the 4s electrons, which is the +2 and the +3 valencies in the case of scandium. The answer to this question, in summary, was the exchange energy, the greater stability due to exchange energy in the case of fully filled d orbital in the case of zinc, which is very stable in comparison to the fully filled 4s subshell. Okay, thank you very much.